The goal of the digital twin is to have a high fidelity replicate of a physical entity to enable two-way communication between them. As the system grows complex, one needs multiple connections to achieve this goal. To remedy this, we propose a data structure to serve as a central building block for building digital twins. The proposed data structure is hierarchical and consists of four levels: the environment, system, components, and attribute level. We use this to build our digital twin, enabling communication between the physical and digital twins using the MQTT protocol. As earlier discussed, we built a GUI to simplify the building process. The build can be direct or can be through the reading of the asset administrative shell. In this instance, we use the asset administrative shell described in an XML file for the UR5E robot. When the file is open, we can see the attributes of the robot described from the database connection to the component systems attributes and the environment using the proposed data structure. With this, we're able to build our digital replica of the physical entity. When we open it in this GUI, there's a builder that builds the digital twin for us, and we can see in the tree view the components of the digital twin. Since we use the MQTT, we have to automatically build the MQTT topic and send these topics to the operators so that we can ensure safe communication between both parties. Once the button is clicked, we have a file of all the MQTT topic needed for our system automatically generated for us. When we click on the Run button, our GUI is populated with the attributes and their live value from the physical twin. We're able to move the physical twin, as you can see on the bottom left, when a change is made in the physical entity. To move by a certain amount of degree, we click on the robot and we click on update and the robot moves. We try the same thing with other joints like the shoulder joint in this instance. We input the value, we click on update and the robot updates. We can set it to another value and the robot updates. With this, we're able to achieve two-way communications between the physical twin and the digital twin. Admittedly, this is not the best way to visualize it, but we are able to use other visualization services thanks to the MQTT protocol. One is a 3D visualization using the RoboDK software. With this, we are able to move the robot for our GUI using the data structure, and we're able to visualize this change in both numerically in the GUI and also visually with the 3D software. This gives us flexibility on how we wish to visualize the evolution of our digital twin as the physical twin evolve. Um, Additionally, we have a dashboard running in the background from Node-RED that is also considered a digital twin service for us, and we're able to have graphical tabular representation, a dashboard representing the different attributes of the physical twin. So when we make changes, we're able to see those changes populated in real time in our system. Now, what about structures that were not built with smart utilization in mind? Well, we propose the use of external data acquisition mechanisms such as the Oracle markers to determine the position and status of the CNC machine door. Similarly to the other digital twin, we use an asset administrative shell to describe what we want to achieve. We have using the data structure. With that, we feed it into our system, and our system builds the GUI for us, builds the digital twin for us. We build the topic, and we are able to see the status. When we make a change to the physical entity, that change is recorded by the digital twin, and it is visualized. In addition to this, we are able to visualize the historical data using a time series database in our historical management solution. So we're able to see how the system has evolved with time. Thank you for listening.